Okay, I'd like to talk about Newman projections and the conformational analysis of alkanes. So we know that it's possible to rotate around single bonds, and this rotation results in the creation of different conformations. Just to show what I mean about rotating around single bonds, uh, it doesn't matter if these are different colors, but this is what that rotation kind of looks like. Right, we're rotating around this single bond. Now there are a number of different ways to represent these different conformations. Uh, we've used the wedge and dash formalism in this class, and you've also used it in Gen Chem. There's also what's called a sawhorse that we're not going to use so much. And then what we're really going to focus on in this video are the Newman projections. And so let's talk a little bit more about these. So the way to imagine these Newman projections, it's as if we were looking down that single bond that we were rotating around. So if we come back to this picture here, so we have right the red carbons or the red atoms on the left, the blue atoms on the right, right. And for the Newman projection, we're going to look down this single bond. And so when I rotate the molecule, this is what we're trying to represent when we draw these Newman projections. And so to represent this in two dimensions, so that we can tell the groups on the front carbon from the groups on the back carbon, what we do is we represent the front carbon by a dot in the center. And so then the full lines coming from the dot to these red groups represent groups coming off the front carbon. And then we represent the back carbon with this big circle. And so then the lines representing the bonds going to the groups on the back carbon are therefore shorter, right? This big thing is the back carbon. And so this is the bond between the back carbon and its groups. So the full lines, groups coming off the front carbon, short lines, groups coming off the back carbon. So if we want to do an example of drawing a Newman projection, so we're looking down this bond. And so on the front carbon, we're going to have a methyl group coming down, and then the other two groups are hydrogens. And then on the back carbon, I've got a chlorine going straight up, I've got a methyl going down into the left, and I'll have a hydrogen going down into the right. Right, so this is the bond we're looking down, and so these are my three groups on the front carbon. Right, the methyl is going down, and then the hydrogens 120 degrees apart from each other and the methyl, and then the chlorine going up off the back carbon. This is going away from us, and so when I rotate it, the methyl is going down into the left, and we've got another hydrogen down into the right. To describe these different conformations, oftentimes we specify what's called the dihedral angle or the torsional angle. And so if we imagine this just being two dimensions, right, this angle would be 60 degrees, and so this dihedral angle is 60 degrees. Now it turns out that there are two really important conformations. There's the staggered conformation, where essentially the hydrogens or whatever the groups are on the front carbon are as far away from each other as they can get with the groups on the back carbon. And so the dihedral angle is as large as possible. When the dihedral angle is zero, so essentially they're overlapping or they're eclipsing one another, these have the highest energy. And the difference between these two conformations in ethane is 12 kilojoules per mole. Now, if we imagine, continuing to rotate around that single bond, right, we can see, right, we start in a staggered conformation, right, we go eclipsed, and then staggered, and eclipsed, staggered, and eclipsed, staggered. And each time, the barrier to this rotation is 12 kilojoules per mole. What we often do is we decompose the total barrier into the interactions between individual groups. And so if the total difference in energy between the staggered and the eclipse conformations is 12 kilojoules per mole, then we essentially say that each hydrogen-hydrogen eclipsed interaction is responsible for 1/3 of that, or 4 kilojoules per mole. We're not going to talk a lot about this, but it turns out in ethane, the reason for the stability of the staggered conformation is due to interaction between the molecular orbitals. And so it's actually an overlap between a bonding molecular orbital from one carbon hydrogen and then an anti-bonding orbital on the other carbon. It's this overlap that gives the stability to the staggered conformation. And when I rotate around that single bond, it removes this overlap and increases the energy. So propane is very similar to ethane, only now instead of having all hydrogens, we have a methyl group, and the barrier to rotation is a little bit higher. In ethane, it was 12 kilojoules per mole. Now it's 14 kilojoules per mole. And so we can actually ask, right, uh, what is the uh, energy due to the eclipsing of a hydrogen with a methyl group? So if we know the total interaction is 14 kilojoules per mole, from ethane, we gave each hydrogen-hydrogen interaction a contribution of 4 kilojoules per mole. So if I subtract out the hydrogen-hydrogen interactions, then the methyl-hydrogen interaction must be 6 kilojoules per mole. So let's do an example. Let's draw the Newman projection for 2-methyl propane and then predict what the barrier to rotation is going to be. So here's methyl, and I've got a 2-methyl propane. And so if we look down this bond, the front carbon is going to have all hydrogens. The back carbon is going to have a methyl group going down, a methyl group going up into the right, and then a hydrogen going up into the left. And so this would be the staggered conformation. If I go to the eclipsed, we can see I get one hydrogen-hydrogen interaction. And so we said that was going to be 4 kilojoules per mole. And then each hydrogen-methyl interaction is going to be 6 kilojoules per mole. So 4 from the hydrogen-hydrogen, 2 times 6 from the 2 methyl-hydrogen interactions. So that would give us a total barrier of 16 kilojoules per mole for 2-methyl propane. Now, butane is interesting. The conformational analysis is a little bit more involved. And rather than just having a single energy for the staggered and a single energy for the eclipsed, we can see that there's sort of 2 different staggered conformations and 2 different eclipsed conformations. Now, what gives rise to the different staggered conformations is actually steric hindrance between the 2 methyl groups. So methyl groups are really big and bulky, and so when we try to make both methyls kind of right next to each other, they actually bump into each other. And so this is called the gauche conformation, right? When the 2 methyls are as far apart as possible, then we call that the anti-configuration or the anti-conformation, and that's more stable because we don't have the 2 methyls bumping into each other. And so this 3.8 difference in energy between the 2 different staggered conformations is a result of this steric hindrance. And then the reason we have different energies in the eclipsed is because I can have the 2 methyls being eclipsed, or I can have the methyls being eclipsed with hydrogens. All right, so we can actually break down the energy costs of these different interactions, and they're given in this table here. So you don't have to have these memorized. If we need to do a conformational analysis, we'll give you the energies due to these different types of interactions. So as a final example, we want to draw the Newman projections and identify the highest and lowest energy conformations. So if we're looking down this bond, I've got 2 methyls on the front carbon and 1 methyl on the back carbon. So on the front carbon, I should have a methyl going down and a methyl going up into the right. So I've got a methyl going down and a methyl going up into the right, and then I should have a methyl going straight up from the back carbon. Now, the other staggered conformations that I can draw would be here and here. And so in this case, I've got a gauche interaction between the methyls. In this case, I have 2 gauche interactions between the methyls. And then in this case, I have just 1 gauche interaction between the methyls. So I think these 2 on the sides are going to be equivalent, and they're going to be the lower in energy. And then this one is going to be the higher energy staggered conformation. All right, and then if we go to the eclipse conformations, so I can have a methyl eclipsed and a carbon, or I'm sorry, and a methyl hydrogen in this eclipse conformation. Again, I've got a methyl methyl, uh, a methyl hydrogen, and a hydrogen hydrogen. And in this one, I have a methyl hydrogen, methyl hydrogen, methyl hydrogen. And so if we go back and look at these different energies, so the hydrogen hydrogen strain is 4, methyl hydrogen is 6, and methyl methyl is 11. So I've got an 11 and a 6 and a 4. So I think that's 21. I've got, I think, the same thing here, an 11, a 6, and a 4. That's 21. And then here I have a 6 and a 6 and a 6. So that's 18. So I think this would be the lowest energy conformation, uh, which would mean that these two are the highest energy conformations.